Greetings, I am Professor Luis Javier Ontañón, and on behalf of my coworkers, I present this work entitled A Piecewise Linear Dynamical System Design for the Generation of Random Sequences with an FPAA. The presentation will be divided in three main topics. First, we will talk about nonlinear dynamics. Second, about unstable dissipative piecewise linear systems and how they are composed. And third, about the electronic implementation using the field programmable analog array. Regarding the first topic, nonlinear dynamics can be acquired principally in the following ways. First, by the multiplication of their states. For example, as it is represented in the Rosler and Lorentz system. In this case, the nonlinearities that this system present result in chaotic attractors that are well known. Also, by means of piecewise linear systems, for example, the unstable dissipative systems as represented in reference number 3, can also acquire nonlinear dynamics with an easy mathematical equation. In this case, the dynamical system presents an affine vector B, which will change values regarding of each domain introduced into the system. These domains will be visited regarding the value of one of their parameters. If the piecewise vector B is designed properly, the result trajectory of the system will present chaotic behavior as this double scroll presented here. The second topic, we will talk about these unstable dissipative systems and how they are composed. First, let's consider this affine system given in equation 1. The matrix A will be composed of real values as it is presented here. In this particular case, the piecewise vector B will be composed of a parameter B subindex index 3. The states of the systems live all in the real values, and the parameter B will also be real. We will divide the space in two main domains. Each one of the domains will generate an equilibrium point, and each equilibrium point or each one of the domains will be visited regarding the value that the vector or the state X takes. The idea is as follows. Let's divide the space of the system in any number of domains. As we mentioned before, we will divide it in two main regions. For each region that we generate, an equilibrium point will emerge. According to the unstable dissipative system theory, in order to generate chaotic attractors as the one presented before, the system must follow this definition. First, the sum of the eigenvalues must be negative. In this case, the system will be dissipative. Second, one of the eigenvalues must present a real negative part and imaginary part equal to 0. And the last part of the eigenvalues will be a complex conjugated part, which will present a real positive part and imaginary part. This will result in the following dynamics. The real negative eigenvalue will take any given initial condition and will displace it towards the equilibrium point. By any small deviation of this eigenvector, the trajectory will begin to oscillate in an unstable plane. When the trajectory starts to increase, it will eventually cross a commutation surface. At the moment of the crossing, we will change the value of the piecewise function, and with this action, we will also change the equilibrium point of the system. After changing the equilibrium point, now we will consider a new initial condition here, and it will follow the new trajectory of the equilibria. In this case, also the negative eigenvector will attract the trajectory towards the equilibria, but any small deviation will make that the system oscillate in this unstable plane. Eventually, it will also cross the commutation surface, repeating these dynamics again and again. The third topic that we will discuss is about the electronic implementation. In this case, the mathematical structure of the piecewise function is simple enough that we can build a circuit diagram without the use of analog multipliers. In this case, all the components represented here are simple operational amplifiers, which reduces cost in the processing. Due to this fact, the circuit can be implemented in a field programmable analog array, or FPAA for short. This embedded system allows a real-time analog processing which fits the characteristics needed in the electronic implementation. The resulting configuration is presented in this figure. Notice that there is no analog multiplier. The voltage solution of the circuit can be measured throughout a simple oscilloscope. In this case, the projection of the states is shown here. Notice the complex scroll attractors. In this particular case, the system presents chaotic behavior, and since the trajectories of the systems are complex, and also that the initial conditions that the system will take when the FPAA is initialized are unknown, the results of the states are completely random. However, in order to process the data and to avoid repeating patterns, the following steps were performed. First, we analyzed the most frequent regions, both in X and Y, and from these values we decided to implement as dynamic. In the left-hand side, we have the histogram for the X data. Notice that the most visited values are near the equilibrium points. And in the right-hand side of the slide, we have the histogram of the Y data. In this case, the most visited region is in the center of the equilibria. Taking in consideration these histogram values, we decided to introduce a lower and an upper bound to convert transitions between into zeros and ones, respectively. In this case, the location of the bounds were selected with the median value of the histogram of the Y data presented earlier. The idea is as follows. Any trajectory crossing the lower bound will be considered as a value of 0, and any trajectory crossing the upper bound will be considered as a value of 1. After the symbolic conversion, a desk queuing technique similar as the one presented in the reference was implemented. Here, it can be appreciated the histogram of both zeros and 1 values, which in quantity are almost equal. Also, to assure randomness, the monobit test was implemented. In this case, the sequence passed. Hence, confirming that the process generates a random binary signal which will be utilized in encryption algorithms as a future work. To conclude this work, it is important to remark the first. The unstable dissipative systems of the type 1 present nonlinear behavior that can result in chaotic multi-scroll trajectories. Also, this particular type of system results in 1 scroll for each domain, an equilibrium point that we add or introduce to the piecewise function. Third, the structure of the mathematical system is easy to implement electronically via a field programmable analog array. And finally, the resulting trajectories of the FPAA can be implemented in the generation of random binary sequences for encryption processes. Thank you for your attention.